Hello everyone. In this video we will go over the Flow team's research progress throughout the fall 2023 semester. Before getting into that, however, we will briefly introduce the members of the team and provide some background as to the goals of the Flow team at the start of the semester.
Hey everyone, my name is Carlos Jurado. I am completing my bachelor's degree in mechanical engineering. I've been a research assistant at the Keck Center for a year and a half now.
Hello, I'm Gabriel Sanchez. I'm doing my bachelor's in electrical engineering and have been at the Keck Center since the start of this summer.
Hello, my name is Omar Rubio. I'm a student mechanical engineer. I have been here at the Keck Center since June of this year.
Hello, my name is Andres Estrada. I'm a student in mechanical engineering. I have been at the Keck Center for 2 years, focusing on pedometry and flow.
Hello, my name is Hugo Estrada. I am doing my PhD in mechanical engineering. I have been here at the Keck for almost 2.5 years and I am the team lead. The overall goal of the Flow team is to generate knowledge to better understand the effects of flow on part quality and defect formation throughout the characterization of flow distribution within different LPVF systems and the analysis of part properties. Specifically for this semester, we divided our attention into 3 main goals. To push towards the completion of our paper, where we attempt to demonstrate that part quality can be improved through the implementation of a different flow configuration, to develop an experimental LPVF enclosure with custom flow configuration to analyze its effects using different setups, and to develop our own flow characterization system compatible with every LPVF machine at the Keck Center and with interchangeable sampling instrumentation. Before going more in detail though, we also have a quick update regarding one project that was pending from earlier this year.
During the summer, we had a trip to Stanford to test several MRV models that we had prepared. One of the models had some complications while we were there, which prevented us from completing the test. During this fall semester, we revisited the design of the model and made some minor changes. We printed it again, assembled it, and were able to leak test it successfully. The only thing that we have to do now is to safely pack up the model and ship it as soon as everyone is ready.
Throughout the summer, we worked on modifying the EOS M290 to improve flow distribution across the build plate and run experiments to test our hypothesis that this new flow configuration would result in better part properties. This semester, our focus was to demonstrate that the modifications done to the optics did not have an impact on scan quality and to analyze tensile test results, part porosity, and plate scan data to determine if there was a statistical difference between builds. Starting with the optics, after several beam measurements on the original modified setups, we were able to identify a difference of 0.02 microns on the average beam waist diameter between both setups, which can be attributed to the tolerance of the measuring equipment. Because of this, we concluded that modifications to the optics were performed successfully without impact to laser scan quality. As for data analysis, things have not gone so smoothly. We performed an ANOVA on the tensile test results and failed to achieve a sufficient confidence interval to claim that the samples were statistically different. Similarly, the analysis of the plate scan data was inconclusive, and the initial XCT porosity analysis revealed a comparable amount of porosities in all 4 samples. These results are not ideal and have proven to be significant roadblocks that interfere with the completion of the paper. Nonetheless, our plan is to continue analyzing porosity to use as our main argument. Just recently, a second porosity analysis was performed on the artifacts and showed more promising results. This study revealed an overall decrease in porosity for the build where the improved flow configuration was used. In addition, it was also noted that the artifact printed closer to the inlet presented significantly less large defects with the corrected flow distribution. A more in-depth analysis is needed for these results. However, we're hopeful that this will make for a compelling argument once polished and presented along with some of the micrograph data that we have. Moving on, we have the testbed, and there's quite a bit to talk about here. To begin with, the idea behind the testbed is to develop our own personalized system with an ideal gas flow distribution, where we can test various flow configurations to analyze their effects on part properties and part quality. The first step for such a project is to come up with a design. We started working on this during the summer, but it was until this semester that we finally settled on a model. The main characteristics of the slotted design, as we call it, are the large inlets and outlet at each side of the testbed, the clear panels that act as front and back walls and provide full visibility into the chamber, and the removable laser-safe windows.
Once we had our design, the next step was to identify the materials needed to build the enclosure. We already had a prototype of the testbed that we received from Taylor Alloys during the summer, but it did not match with our requirements and had to be modified significantly. First, we focused our attention to the optics adapter, which connects the testbed to the scan head. We decided to use a design that matched with one of the Aconity one, with the main difference being the maximum size of the coupling. After adjusting the size and making sure that the mechanism was able to connect without any issue, we purchased materials for the top plate and machined it to match with our design. Lastly, we identified a company that could provide us with the custom-sized laser shield that we needed and placed the order, which allowed us to complete the top plate assembly.
After that, we spent some time looking for suitable laser-safe windows, which proved more challenging than we initially thought due to the size requirements. But eventually, we managed to find a provider. While working on this video, we submitted an order for 2 more components: a glass panel that will be used for the walls of the testbed, and an aluminum bar that will be machined to produce the rails needed to hold the laser-safe windows. Once we have all the components, we will assemble the first wall, which will serve as a proof of concept to ensure that the design is robust. Having done that, the next step will be to purchase the second half of the materials and assemble the other wall.
In addition to developing the enclosure for the test bed, we have also been working on a separate monitoring system which will serve to detect the presence of soot particles within the chamber while printing. We call this system the photodiode circuit, and our initial plan was to use pre-assembled photodiodes from Thorlabs. However, after some testing, we noticed irregular behavior and decided to build our own circuit. This light detection circuit is capable of detecting any changes in light intensity in the nanosecond range and can be divided into 4 categories. Each category serves a specific function in order to create an optimal environment in order to obtain accurate and consistent results. The first part of the circuit consists of a voltage regulator. The second part of the circuit was a low-pass filter in order to prevent any high frequencies from passing to the output. Noise will be generated by batteries or power supplies. Because of that, we will make sure that we can attenuate those undesired high frequencies. The third stage of this circuit consists of understanding the behavior of the photodiode, according to whether if it's in reverse bias or zero bias. Design depends highly on the response given by the photodiode, and there are various ways to calculate the current generated by it. The most common one is using the spectral response of the photodiode. The fourth stage consists of amplifying the current generated by the photodiode. During this stage, the direction of the current determines the positive or negative voltage. The amount of voltage is then determined by the feedback resistor that amplifies the current. The capacitor ensures there is a low-pass filter and a stable circuit due to the internal capacitance of the photodiode and transimpedance amplifier op-amp. By now, we have gone through this entire process on a breadboard and demonstrated that the circuit is operating properly. For the next steps, we plan to solder the components onto a PCB to reduce the size of the circuit. Repeat the process a few times to build an array of photodiodes. And lastly, to design a housing for the components so that they can be mounted on the outside of the testbed. Aside from developing the enclosure, we also had to design the flow circuit and define the sensors and additional components that we would be using. That took a few iterations and ended up looking like this. As you can see, we have sensors for flow, pressure, temperature, humidity, and oxygen as part of the monitoring system. Pressure relief valves, manual valves, and solenoid valves for safety, and blowers, heat exchangers, and filters for general gas flow circulation.
Looking specifically at the flow circulation component, it became obvious that we would need something different from what is normally used in LPBF systems. To begin, we'll start with our blowers. These are much larger than the ones in the Econity 1 and are capable of generating a much higher flow rate. Because of this, we decided that an entire new filtration system would be necessary as the previous one did not have sufficient capacity. Identifying a new system has been a slow and ongoing process, with many filters being either unable to meet our requirements or are more industrial level than what we need. We are currently in communication with a few companies that seem promising. One of them is the one that provided us with the blowers, and the other company, the one that provides the SLM. We will keep pushing and hope that by early next year we will be ready to place an order.
Other than the filtration system, we also started thinking about the heat exchangers. We wanted to make sure that one will have sufficient capacity. At first, we planned to design them ourselves by using as a reference the one used for the Raining Shop. Soon after, we realized how complex and time-consuming this task will be, and shifted our efforts into locating a provider that could fulfill our requirements. In doing so, we found the same provider that is used by Raining Shop, and were able to identify suitable heat exchanger models. For now, we're pending confirmation to place the order. Once we do, it will take a few weeks for the parts to arrive, and as soon as they do, we'll move on the next part of the project, the assembly of the flow circuit.
To get an idea of the materials needed for this step, as well as the overall footprint of the system, we had to design a CAD model for the entire assembly. We first worked on creating a stand for the two blowers, where the blowers incorporated a system were stacked on top of each other to maximize space. The design features mostly McMaster quad T-slot components for ease of access and quick turnaround times. There are 4 main posts held to each other at 3 different levels. The blowers themselves are held up by 2 quad beam cutting across. Between the beams and the blowers, we have a vibration dampening mount to help minimize unwanted movement. The bottom holds 4 leveling plate casters with adjustable heights and including dampening material as well. The necessary components were compiled and currently pending purchase. As it sits, this is the current testbed configuration. This model features all major components with the exception of additional sensors that will need to be finalized. The entire system uses a 4-inch diameter piping with quick clamp disconnects for ease of access and uniformity. Using this model as reference, we can estimate the testbed assembly will have an area of 4.7 meters by 6 meters with a height of 4.2 meters, although the dimensions may change depending on the filtration system that we end up using.
Recently, we focused our attention on preparing the Economy 1 for mounting on the testbed, which required us to disassemble the lid of the machine. Even more recently, it was decided that the system should be relocated to the Cotton facility to have more available space to work with. Because of this, the entire team has focused on disassembling the Economy 1 into sections to facilitate the moving process. As of the making of this video, the system has been disassembled into 3 main parts and wrapped up in a layer of plastic to prevent any components from falling out. All of the smaller parts have been organized in boxes, and we are waiting for the relocation of the system. As soon as that happens, we will fully focus our attention on the installation and reassembly of the system. Now, we'd like to tell you about the build cavity assembly, or as we have decided to call it for now, the In-Cavity Flow Characterization System, or IFCS.
The IFCS is an amalgamation of sensors and motor drivers that permit us to characterize the flow of certain LPVF systems with minimum disruption using pirostatic tubes. Taking advantage of LPVF build cavities, the IFCS is designed to fit inside them. At this moment, we can test the SLM280, EOS M290, and Renisha. But in future work, we want to add the Economy MIDI Plus. The work on the IFCS began before I fully integrated into the flow team. Up to this point, we already had purchased the components, which includes National Instruments microprocessor MyRio, an absolute pressure transducer, a thermistor, 2 motor drivers, 2 linear guide rails, stage rails, 2 pressure transducers, a battery power bank, a USB-C power delivery trigger board, and 2 pirostatic probes. Additionally, a lot of work was done on the wireless connection between the computer and MyRio. Now, talking about the design. At the beginning, we were given an initial assembly of what Dr. Elkins envisioned. This initial assembly had all the components that needed to be manufactured without exact dimensions. How all the sensors will fit in the IFCS wasn't a priority at this stage, since we were just focusing on designing the structure that will hold the linear rails. Our most important constraints were the different cavity dimensions of the targeted LPVF systems. The system with the smallest cavity will become the constraint. In our case, it was a combination of Renisha's build plate area and the EOS cavity height. Unfortunately, due to the Economy's build plate circular shape, it was not possible to include it in this design. The top plate, besides its function as a substitute for the build plate, also has an open slot to permit the travel with the piro probes. Although we call it the top plate, we have 2 different variations, with the difference being the location of the slot. The differences in the slot position permit us to characterize flow in different areas of the build plate. The bottom's plate only job is to hold some of the components and, more importantly, connect to the system's build platform. Since each LPVS system has different approach mounting the build plate to the platform, we decided to have a single bottom plate with an additional custom connection plate for each LPVS system. For the EOS, we machined this connection plate, but for the SLM, it was printed with resin on the Neo 450 with similar success. To permit the probe's horizontal and vertical movement, we used 2 linear stage rails. The linear gate rail head has mounting holes that we use to attach the C-axis vertical mount, where we mount our second linear guide rail. In combination with 3 brackets, they form the probe holder assembly, where the pyro probes are mounted at a 100mm distance from each other. To hold the probes in place, we used 2 components: the back section of the subassembly, which connects to the linear guide and has a semicircular cut to position the probes in each corner, and the front section, which has the same semicircular card along with a counterbore hole where a screw can be inserted to clamp the pewter probe. With all the components ready, and after some back and forth creating the technical drawings, we contacted a local machine shop to manufacture the parts. After finalizing the design, we needed to find a configuration where we could mount all our components without disrupting the probe's travel path with the 3 different slots positions. To facilitate this task, we recreated all the components in CAD to better visualize the arrangement. With assembly, we were able to test different configurations until we found a sweet spot between ease of assembly and space for the probe's movement. With the help of the T-slaughter parts, we created different fixtures that could be mounted onto all the components while utilizing the available space. When the machine parts arrived, we started assembling and wiring all the components. This step was the most labor-intensive, and with Darko Enkin's input during his visit, we finalized the first version of IFCS.
Working in parallel, we also developed a code to operate this entire system using LabVIEW. This way, we're able to control the initial and final positions of the sampling instruments, resolution of the measurements, and the sampling speed. Additionally, once the program is finished taking measurements, it automatically produces 2 files, one with the raw data of every sensor and one with the corresponding units. This way, it is less time consuming to process the results, but we are still able to go back and double check everything in case something doesn't add up.
Before talking about some of the results, we wanted to mention how the IFCS characterizes flow. First, we use spider probes connected to their corresponding pressure transducers to determine the local pressure. By knowing the maximum voltage output and detecting range of the sensors, we can obtain the dynamic pressure at a given location and substitute that value into Bernoulli's equation to find the velocity. Since density is one of the variables in the equation and its value changes depending on atmospheric conditions, we also need to know the atmospheric pressure and temperature. To obtain the value of the atmospheric pressure, we use an absolute pressure transducer, which gives us a voltage reading that is then converted to pascals. For temperature measurements, we use a thermistor, where the resistance will change depending on the temperature. Using a voltage divider with the thermistor and a known value resistor, we can obtain the thermistor output resistance. To convert the resistance to temperature, we use the Steinhart-Hart equation, where T is temperature in Kelvin, R is the resistance in ohms, and A, B, and C are the Steinhart-Hart equations that vary depending on the type of thermistor. With all the necessary variables obtained and substituting the values into the equations, we can calculate the velocity of a gas at any given point. Some of our findings include this behavior in the SLM280, where we see an increase and decrease of velocity at the plate's edge on the bottom inlet. So far, we successfully tested the IFCS in the SLM280 and EOS M290. We plan to test it in the Rennie shop before the semester's end.
And with that, we can wrap up the Flow team's research progress for the fall 2023 semester. Happy holidays and see you next year.